First definition. In mathematics and in science, we've always liked to standardize things so that if I tell you something, you know exactly what I mean, rather than just sort of have an idea of what I mean. And this caused problems, like historically, our measurements were somewhat problematic. Like, where did the measurement of a foot come from? From someone's foot. And usually it was the king's foot. That's the official foot that we're going to use. But then if someone said, yeah, you're going to buy, maybe you're buying some material, it's 5 feet long. And you'd be like, oh, the king's feet are really short this year. When we had the old king, it was like this. And then we have a problem, what happens if the king dies and now it's like a baby king? Do we use that foot? And it's like, just like, this is problematic. It's a good idea because people's feet are relatively the same size, but not exactly the same size. So there became a need to standardize things. So that if I tell you, hey, draw an angle of 100 degrees, you're like, well, where do you want me to draw that? How do you want me to draw that? So we have angles in standard position. And there's one very, very important thing for an angle to be in standard position. It must start on the positive x-axis. So if you define where something starts, right, then 100 degrees becomes like, okay, I know where you're starting from, I can measure 100 degrees from there. The next important thing is that, right, one person says, well, I'm going to go 100 degrees in this direction. And another person says, I'm going to go 100 degrees in this direction, and now they're different again. So there has to be a second sort of rule to angles in standard position. We decide that if we are going counterclockwise, that's positive 100 degrees. Clockwise would be negative 100 degrees. So an angle in standard position starts on the positive x-axis, and positive angles go counterclockwise, negative angles go clockwise. Is the diagram enough, or do you need me to write that out in words? Are you okay with that as a diagram? So there's our definition of angles in standard position. So if someone says, I have an angle in standard position of 200 degrees, then you know where it ends. And when talking about things, we split the whole thing into 4 quadrants. We call this one quadrant 1, this one quadrant 2, this one quadrant 3, and this one quadrant 4. And I don't know why, but they're often labeled with Roman numerals. Like, there's all these like weird traditions. It's not bad. If you did Q1, Q2, right? If you wrote Q3 for this, perfectly fine. If you wrote Q for quadrant and then did Roman numeral, perfectly fine. Okay? So we start having to have definitions so that when someone's talking about something, they're doing the same thing, which becomes really important in science and in mathematics, so that people aren't getting different answers or different results and confused by each other's results. Sort of like, I got this, I'm sure I'm right. And the other person's like, I got this, I'm sure I'm right. And they're actually both right, but they were using different definitions for how things work, and it's really confusing. Okay? mathematics used to be really, really fussy. And we're still, we're still fussy, but we're not nearly as really, really fussy as we used to be. So, for example, now in grade 12, if you get an answer that's 5/15, you can leave it like that. You don't have to simplify it to 1/3. We'd understand that they're the same thing. But historically, if he wanted everybody to get the same answer, it would have to be in simplified form. So all textbooks, when they wrote their answers, there was rules for simplification right down to every single situation you'd run into. There was rules for how you'd have to write your answer. Because as we get to more complicated things, there's going to be so many different ways you could manipulate your answer and write it. So, definitions are important. This is angles in standard position. Next, a review. What are reference angles? Okay. So reference angles are super important for solving trig equations. They are the angle. So here's a picture first. If I have an angle in standard position, like the 100 degrees I had before, so here's my 100 degrees. We call where an angle ends the terminal arm. So I guess angles have arms. It's kind of weird we give body parts to things in math. Angles have arms, triangles have legs, squares have sides. I don't know. I'm not sure. But we call that the terminal arm of an angle. And your reference angle is always going to be a positive angle. So first of all, it's never a negative. So it's a positive angle between the terminal arm and the nearest. And I'm going to change the color here because this is important. It's not the nearest axis, it's the nearest x-axis. Because sometimes, like this 100 degrees, you'd be like, oh, that 100 degrees is so close to my y-axis. Maybe I should make my reference angle 10 degrees. No. Your reference angle is always to the nearest x-axis, and we will be using like a little r. So if the angle is theta, then my reference angle would be theta with a little r. If my angle was x, my reference angle would be x with a little r. So whatever variable you used for your angle, your reference angle has that. And you have to figure out what angle is left. So a little bit of mental math here, right? If this is 100, what angle would be left to get my reference angle? 80 degrees. Because it has to add up to 180. And so whichever quadrant you're in, you sort of have to do a little bit different mental math. Does it make sense that in quadrant 3, you would have to take whatever, like if I took 200 degrees in quadrant 3, my reference angle would be 20, because I would do 200 minus 180. And a little review of why reference angles are so powerful. Okay? So here's a review of grade 11. It's always nice to get a little bit of review. Remind yourself of stuff that you've done already. So what I'm going to do is I'm going to take, well, even choose one that we should be able to do without our calculator as a review from grade 11. So the angle I'm going to pick in quadrant 1 is 30 degrees. In quadrant 1, does it make sense then to back to the nearest x-axis, your reference angle is 30 degrees. In quadrant 2, I'm going to choose 150 degrees, so my reference angle, right, that's to there. Here my reference angle, back to the nearest x-axis.
Thank you.
You're welcome. So it doesn't matter which way you put the arrow for your reference angle, because when we label a reference angle, it's positive anyways. So I can put the arrow this way or that way. I'm not changing positive or negative. Positive or negative angles is when we're talking about standard position. So that's 30 degrees there. In quadrant 3, if I had started with 210 degrees, again, that would be my reference angle there. My reference angle would be 30 degrees again. And finally, if I went in quadrant 4, 330 degrees, my reference angle, once again to the nearest x-axis, would be 30 degrees. And the reason reference angles are so powerful is because they allow us to do trigonometry further on. Yeah.
What's the second number?
This number here, it's 150. I'll make it a little neater. There we go. You're welcome. What makes this so powerful is, see if you remember these. Do you remember what sine of 30 degrees was? What cos of 30 degrees was? And what tan of 30 degrees was? Because these were ones that you were expected in grade 11 to memorize. And there were strategies to do it. Now if we went to our calculator and typed this in, you would get 0.5. So sine of 30 degrees is a half. Okay? If you went to your calculator and did cos of 30 degrees, you would get, I think, 0.866. I don't have the decimal memorized very much. But it happens to be, well, I'll do it. I'll stick with decimals to pretend we forgot that, because I'm looking at you guys, and you guys are saying exactly that. Yeah, I forgot that. Cos of 30 degrees. 0.866, I got that one. 0.866. I will remind you, that's square root of 3 over 2. And tan of 30 degrees, that's 0.577. These, of course, are rounded. And you might, when I show you the numbers, like, okay. But you might not know how you get those. We'll do that again, don't worry. I'll remind you where those numbers come from when we have to memorize these again this year. Okay? But then, with that in mind, when we look at sine, cos, and tan of 150, we get exactly the same numbers, 0.5, I'm going to go all decimals, 0.866, 0.577, but these two are negative now. So kind of interesting, if you have the same reference angle, sine, cos, and tan, the values stay the same, but now sometimes things are positive, sometimes things are negative. And if I go to quadrant 3, and I do this again, sine of 210, cos of 210, and tan of 210, the idea is if you knew sine of 30, cos of 30, and tan of 30, you know these ones, because they're exactly the same numbers again. 0.5, 0.866, and 0.577, but this time, those two are negative. And finally, when I get to the same reference angle in quadrant 4, the numbers turn out to be the same again. It's fascinating. Okay. People who like math love whenever patterns start to happen. They're like, this is cool. Maybe there's something I can explain about this. And in quadrant 4, the numbers are the same, but this time, and so if I circle the ones that are positive, I have cos being the positive one here, tan being the positive one here, sine being the positive one there, and all of them being positive there. This is what we call the cast rule. The cast rule's connected to reference angles, but the cast rule gives us a letter and says, in quadrant 1, all of them. In quadrant 2, only sine. In quadrant 3, only tangent. And in quadrant 4, only cosine. And then how does this help us solve things? Well, you would have got questions like this. Solve for x, where x is between 0 and 360 degrees. And they would tell you, maybe we'll go with cos of x equals negative 0.3. So, what do we know? We have a triangle with an adjacent side over hypotenuse equal to 0.3. Maybe that triangle is 3 over 10. What we need to find is the reference angle. And when we find the reference angle, this is a review again of grade 11. Because reference angles are always positive, and the reference angle for any answer is going to be exact same number. When we find a reference angle, we always plug in the positive value. That'll take us to quadrant 1. So I go to my calculator, and I've got a calculator built in here somewhere. I'll open it up. There we go. I'm going to make sure that I'm in degrees for this one, because we're thinking degrees right now. Okay. And I'm going to go cos inverse of 0.3 and push enter. And I get a reference angle of 72.542. Hey, this is good. I can introduce you to something else that's important this year. Did I get those decimals all right? Did I remember it? 72.542? Yes. When using your calculator, you're expected to have 3 decimal places all the time. Okay? When doing your work, you're expected not to round. So even though I wrote 3 decimal places when I show my work, I keep all the decimals on my calculator until I'm done. So I never round early. Rounding early, you're going to find out, is an E6 error. Not having 3 decimal places is an E6 error. All of your rounding errors are E6 errors. When dealing with degrees, we always have to have the degree symbol. If a question has units and you decide not to write the units, that's an E5 error. Anytime you have no units, they'll be like, you forgot your units. And on all your quizzes during the year, I'll start writing them down. I'll be like, oh, E5, E2. Some of you will collect them all. And then hopefully by the time we get to the exam, you're not making some of those mistakes. So, there's our reference angle. Then, according to our cast rule, we want to find the actual angle x from 0 to 360 degrees, and our cos value was negative that means it has to be here or here. Why? Because this tells us where things are positive. So if cos is positive in quadrant 4, it can't be negative in quadrant 4. If they're all positive in quadrant 1, and cos is negative, it can't be in quadrant 1. So now I know that it's in quadrant 2 and quadrant 3. Sometimes, like, you can draw a picture of it now. You can draw a picture in quadrant 2. You can draw a picture in quadrant 3. These are the answers we're looking for. The standard angle in quadrant 2, the standard angle in quadrant 3. What do you know? You know that this reference angle right here, that's our 72.542 degrees. This angle right here is your reference angle, 72.542 degrees. And your job is to find out what x is. So how could I use this 72.542 to find out what's left? Does it make sense in quadrant 2 that you would take the whole thing 180 degrees and minus your reference angle? Okay. These formulas I never suggest memorizing, because if you draw the picture, it's obvious. And then technically you'll have it memorized, but you'll memorize it because it makes sense. That's going to be a goal for a bunch of things this year. If you remember something because it makes sense, then you'll remember it longer. If you just memorize a bunch of rules that you have to use in certain situations, I guarantee you will forget them, especially when you're under pressure and like, ooh, I need to solve this on a test, and now I don't remember. So as much as possible, these diagrams, I draw them in my head. If I'm doing a question, I'm like, oh, I picture it, and then does it make sense here that in this one, I'm going to go the whole thing. To find this whole thing, I would have to say, I have to do 180 degrees. Oops, I'll do it in a minute. 180 degrees is up to here, but then I would have to add my reference angle to get the whole thing. So I would go to my calculator and do these things. Some nice things about your calculator. One, you could do, so I have a 180, I can hit subtract, and there's an answer button right above the negative here. So if you have this calculator, I can do 180 minus my answer. That gives me one of my answers. And the other one is 180 plus, oh, but now I can't use the answer, but I can actually use this, highlight it, push enter, instead of retyping it. All of these things are going to be super important for saving you time. So 107.458. 107.458. And the second one was 252.542. If you struggle with writing things down, like some people just like flip two numbers around, then there's an E7 error for that. You can't write things down correctly. E7. It happens all the time. You wrote something down wrong. Right? Have you ever done that? Have you ever had a question like you're in grade 2, question says, what's 5 plus 3? And you write 5 plus 2 equals 7. You're not wrong, but that's not what the question asked. You just wrote it down wrong. They have an error for that. That's the E7 error. Half a mark off for just writing the question down wrong. Now, don't think you'd be like, it is not allowed in grade 12. Be like, oh my goodness, this question is way too hard. I have no idea it's worth 4 marks. 5 plus 2 equals 7. I hope they just think I wrote it down wrong. No, if you make the question completely different and way easier, you don't qualify that. Don't I just lose a half mark for writing the question down wrong? No. Not a bad thought, but no. Okay, so those are our reference angles. And definition number 3 that we're learning today. And this hasn't come up very much in grade 11, so this is somewhat new. I'll give you an example first. We would say, yeah, I like 100 degrees, so I'm going to draw 100 degrees again. 100 degrees is coterminal with negative 260 degrees. It is also coterminal with (460 degrees). And the name of what we're doing here, coterminal, kind of is the definition. Sometimes what we name something sort of tells us the definition. Remember I told you what the terminal arm is? The terminal arm is where the angle ends. So coterminal angles are angles that all end or share the same terminal arm. So angles that share the same terminal arm. So there's your, I'll put it, basically they end at the same place. Right? If they end at the same place, they're coterminal. So we're just worried about where they end. Okay? That doesn't mean the angles are the same. Right? If I am skiing and I go over a jump, it'd be really impressive if you saw me do a 360. It'd be really impressive if you saw me do a 720. Right? Normally when I go over jumps, I do zeros. But I'm worried about landing. I'm scared if I would do a 90. Going over a jump and turning 90 is not a very good idea. Then you crash, right? So you end in the same place, but obviously in skiing the 720 would be more impressive than the 0, but that's the idea of coterminal angles. If they end in the same place, all the mathematics that happens at that place is the same. So now we go back to our coterminal angles, and I can get you to do impressive math. Like, what is sine of 390 degrees? Well, it ends in the same place as 30 degrees. And so since I know that sine of 30 degrees is a half, I will now know that sine of 390 degrees is a half. And this is going to extend our trigonometry past 360 degrees. It allows us to do math of, like, I could do sine of 3,630 degrees. Type it into your calculator. You'll get 0.5. Just sounds really impressive that we did extended math, but I just did 360 10 times around and added 30 degrees more. I'm going to be coterminal with 30 degrees and get the exact same answer. So angles that share the same terminal arm are coterminal. And then we're going to get some fun stuff happening. Okay? You will get questions like this. Write all the coterminal angles to 100 degrees. I listed 3. Keep going. Write them all. What's the problem here?
They're infinite.
There's an infinite amount. So option 1 is this the last assignment you will get in your life, and none of you will finish. And you can't leave class until you're done. That would be terrible. And all you do is start writing. And page after page after page, you'd have an infinite amount. Okay? But we have to come up with a way to write all of them. So we sort of make a formula. And the formula works like this. If you start with 100 degrees, mathematically, how could I get to 460?
Plus 160.
I'd add 360.
360.
Right? Does that make sense? How would I get to 260 from 100? I'd have to go backwards 360. And if I wanted to find the next one after 460 in the positive direction, does it make sense that I would have to add 360 degrees again? So, the formula works like this. It says you can add 360 degrees as many times as you want. So I go times by, and I'm going to pick a variable, and I'm going to pick the letter k. Seems like they like to use the letter k for this situation. Can k be 0.3? No. K has to be 1. You can add 360 once. Can you add 360 twice and end in the same place? Yes. How about 2.5 times? No. K has to be a whole number. Can k be negative? Can it be a negative whole number? Yes. Because if I did -1, well, adding a negative would be the same as subtracting. So I could have written plus or minus here, but generally we write plus, and then we say that k has to be a positive or negative whole number. What are those numbers called? They're called integers. K belongs to the integers. When we want to say k could be any number, you know how we use that r for all the real numbers? Does anybody remember the symbol for integers? No. Perfect. We're learning stuff. We're reviewing stuff. It is a fancy Z with 2 lines.
Sure.
Sure. It comes from the German word for number, Zahl, which starts with do-do-do-do-do. A Z.
Why can't
Yes.
it just be 9?
Sometimes it's used as an I, but internationally, it's a Z. So again, like, English was using an I, Germany was using a Z, different place, like, mathematicians, when they're using symbols, want to standardize things. Yeah, there's like a whole history of standardization. And sometimes words have actually changed because one person screwed up and another person, and then it became more popular, the screw up became more popular than the regular word. Like, I know one example of this. You probably, I don't know, maybe some of you know what shape that is. It's a trapezoid. It originally was called a trapezium.
I like that. Sounds fun.
Sounds fun.
Sounds like an element.
And a trapezoid was something else. But then, in a translation of a textbook into English, an American translation actually, I think of a British textbook, the American made a mistake in translating and called the trapezoid, called the trapezium, a trapezoid. And then there was like arguments. Some people were saying trapezium, some people were saying trapezoid. Right? Tomato is getting bad. And then trapezoid won. And you never hear about trapeziums anymore. So,
All of that must be-
Z1 for integers. That's the international symbol for integers. So this becomes a formula, and it sure is better than writing out all infinite amount and doing that for the rest of your life until you're done. Okay, so with that, we can go to example number 1. Part A. Determine the measures of all the angles in standard position between negative 800 and 800 coterminal with 85. So I'm going to draw 85 right here. There's 85 degrees. And we want all of them, and we have to sketch them all. Nice. So, all right here. Technically 85 degrees is coterminal with 85 degrees. Does it end in the same spot? Absolutely. If you added 360 degrees, mental math, what would you get to? 445 degrees. If you added 360 degrees again, what would you get to? 805 degrees. But then reading my question, I'm going to put a line through that one, because I'm only supposed to go up to 800. So I'm going to draw, here we go, in green, (445 degrees). Next, negative. Can we go negative? Yes. Okay. What's negative 2? If I subtracted 360, I would get negative 275 degrees. I'll draw that one in red. And if I subtracted 360 again,
635.
negative 635 degrees. And I'll draw that one in purple. And can you see if I subtracted 360 again, I would get past negative 800. So we are done. Now, something just happened that you didn't even notice. When I was drawing all of those spirals, I successfully put most of you into a hypnotic state. Right now, you are all in some sort of hypnotic state. If I clap my hands, you'll come out of it, and you won't remember anything of this last little bit. But I can influence you a little bit, like with certain things, like you like math, right? You like math. You are going to probably over this weekend feel like, feel like doing math homework. It'll just be like, this normally hasn't happened to me, but now I start to feel like I want to do some math homework. Maybe I'll work on my next take-home quiz, and it's going to be fun, and I really enjoy it. So you won't remember this. All right. So there's part A. Part B. If you wanted to write all of them, we do that idea where we start with the 85 degrees. We can add 360 degrees as many times or subtract it as many times as we want. So we introduce the variable k, and we make sure that we define that k can't just be any number, it has to be an integer. All right, circle questions 4 and 5.